a value function which is not as important as the other two. Well, the absolute value is absolutely most important of these. So it comes up again and again. These are the other two are mostly examples of what you can and might do with the piecewise defined idea. But typically we will have one single formula. Okay, so the next topic is something else, and that is transformations of functions as transformations. Okay, where are we? Functions as transformations, and vice versa. Transformations as functions. So let me quickly review of what the two main things that ways to think about functions, and that's number one is motion. So y equal f of x time, y location. Very convenient way to think about a function, which typically you do have interpretation of the function that you're given, possibly some kind of interpretation from real life. Okay, so that's a typical situation. If not, then that's how you can interpret it and then get something tangible behind it, like a metaphor. Okay. Secondly, it was just graphs. So a graph is a function. Function is a graph, which is really not true, but it is convenient because the graph gives you something tangible. Okay, so you can see what's going on, and it is literally a picture. Okay, so motion, at least you have to imagine it in your mind. The third one is transformations. That's new. Transformation of what? Of the real line. Okay, so we saw just a little bit of that very recently when we talked about symmetries of graphs, and we talked about certain motions of the plane, and they were like, remember, flipping, rotating, things like that. That is certainly is complicated in the sense that it is a plane, and we will be talking about something much simpler. We will be transforming our x-axis. So real line is the x-axis, and it might be transformed in a number of ways. And that is the building block of later on. We'll examine that symmetries of functions in a more precise way once we understand functions as transformations. Okay, so let me start with that. Okay, so once again, graph is not a function. Function is not a graph. Graph is just a way to visualize functions, and but the function is a match between x's and y's. So to begin with, we think of functions as match our correspondence between x's and y's, or from x's to y's, because we remember one is the input, the other is the output. So they are always those arrows. So and now we speak of numbers though. So we did that thing with arrows. Remember, remember this. Just a minute. Well, where is it? One of those. Yeah, the arrows. The arrows. One said, the other said, and there are arrows between them. The arrows kind of faded away when we started to talk about numbers, but it is not. There is nothing wrong with that. I could still think about set x here, and set y there. It just happens that we prefer to put them in the perpendicular way in the Cartesian coordinate system. And that way we can establish correspondence between them. So that way is in our toolbox, and this is just another tool in our toolbox. Is now if there is no Cartesian system. It is very convenient, but there are other ways. and yeah, just a really different angle of looking at things. And then we could have exactly the same thing. There are numbers here, say 1, 2, 3, 4, 5, and here also 1, 2, 3, 4, 5, and we could still have arrows like this. Okay, so that's the correspondence that my function f corresponds. X is on left and x to y is on right. Okay, so as long as there is only one arrow originating from every point on the left, then you have your function. So that's fine. So where is the transformation? And then when you put them side by side, you can see the idea why it is a transformation, because it is like you take the x-axis and do something to it, and then place it on the y-axis along those arrows. So as an example, let me give you a specific function treated this way. So x's and y's. And how about, so once again, I have 1, 2, 0, 1, 2, 3, 0, 1, 2, 3, 4, 5. Here's a function. 0 goes to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, and so on. Okay, so that's my function. Let's ignore the idea of what the formula is. It's really then we'll get back to that. But what can you think of this as a transformation? So think about the x-axis as a whole now. We know where every number goes on the y-axis. So what has happened? What has happened to the x-axis? Well, one convenient way, if this is any guesses what this is supposed to mean? So x-axis, think about x-axis as something tangible. Okay, I have a picture here. The idea is, okay, where is it? One way to, where did I put it? One way to do it is imagine x-axis as or one axis as how about a pencil? Okay, and just you see what have happened to that pencil. Okay, pencil. Where's my pencil? Okay, a pencil with numbers on it. So that is my x-axis. Okay, and then we see what happens to it. Okay. So let me take that pencil and copy it and see what the correspondence is. Okay, so suppose the one on top is the original one and the below is the new one. So what has happened is every number goes to one larger. So 5 goes to 6. So this is what's going to happen. Okay, like this. Okay. You see what has happened? Well, actually, I meant the other way. The top one is the original. So this is the correspondence that I've been talking about. Is this? This. Okay. Okay. So 1 goes to 2. That's my arrow, and 0 goes to 1. That's my arrow too. Okay. So that is the correspondence that we see over here. It can be described easily by a formula. What is the formula? F of x is equal to
x plus 1.
X plus 1. Okay, so the algebraically it cannot be any simpler than that. Once again, I intentionally ignored the possibility of citing this function with its graph, but this is a different angle. Okay, different angle. We're looking at whatever happens to the x-axis how it turns into the y-axis. It is a transformation of the x-axis. It's not transformation is a strong word. For the time being, it is a shift. Very, very simple shift of my x-axis, and then it matches, and that's what the y-axis is. So like you can see, the correspondence, I aligned them, and so that you can see the input at the bottom and output at the top. Okay. So as you can see, what has happened is the shift of our x-axis to the left. So how do we make x-axis into the y-axis? This is how we shifted one unit to the left. Even though we're adding one means that everything is shifted to the left. So that's one example. If you add 2, they will be shifted by 2 units. 3 by 3 units. If you subtract 3 units, the shift will be in the opposite direction. So all of that can happen. Okay, to begin with. So that is if you want to think in terms of something tangible. So a pencil is probably best I can think of. But generally, this is the idea. The pencils are our axis, and you align them in any way you want. But then the arrows indicate where every number goes, and that is a transformation. So if you can almost see how the x-axis is being taken over here like this, right? Just the way I did it. Well, I have too many. What happened here? Let me make a clear. So I take my x-axis. What happened? Nope. It doesn't want to do it. Okay, so let me try to do it literally as the. Oh my God! What are you doing here? Okay, so that's my x-axis with the numbers, and then I'm moving it along the arrows. So 4 starts, the arrow is there, and I'm moving along the x arrows, and then that's how we end up over here. So 4. This is where 4 is. It was 4 ends up at the location of 5. 5 is the location of 6, and so on. Okay, so that is the transformation that I'm talking about. It is the simplest example. It is the simplest example of the transformation that you can see. But once you start thinking more about other functions that we have seen, we can see more interesting examples. So 1 shift 1 unit left. Okay, so that's what happens to the x-axis if you add 1 to x, and so that is your y. Okay, so and then plus 2 shift 2 units right. Okay, so now let's do more example. What about y equal f of x equal negative x? What does that do? So I'll just copy this. Copy. Paste. Okay. So let's if it's unclear, and that is the point. After all, what we do is we just draw more arrows. Okay. So let's draw arrows. -1, -2, -3. -1, -2, -3. Okay, x and y axis, and the correspondence is drawn with arrows. So 0 goes to 0, 1 goes to -1, right? 2 goes to -2. -1 goes to 1. -2 goes to 2. Okay, do you see what's happening? What kind of transformation is this? It is a flip, yes. It is a flip upside down. So the x-axis, if you take the x-axis and flip it upside down, that's what's going to happen. So literally, every number will be there's a flip about the origin. Flip about the origin. Flip about the origin, and then once you do so, nothing happens to 0. It stays put. So it's literally, you can think of it as rotation 180 degrees. You can once again try to accomplish that with this. So let me try to do that. So if I take this one, and well, okay, that's to the best of my ability. So I'm flipping. So it is a mirror image, unfortunately, but otherwise I have to, where's my 0? I align my new pencil with, I align zeros, okay? And as you can see, the correspondence then is there. So this is where the correspondence is 0 and -1. 0 and -1, 1 and -1. -1 and 1, these are the correspondences. Okay. So we have right now a flip and a shift. So for these two transformations, that are really not, once again, too strong a word to use. Transformation. In reality, it is the shift and flip. They're called motions. Why motions? Because you literally move things. Transformations, it's something bigger or more complex. And what kind of transformation you can think of other than motions? So the motions is literally you take an object and you move it. Okay, nothing happens to the object. So can you think of transformations that are more severe to the object? Say, well, so don't think pencil anymore. Well, let me see. Okay, well, say a piece of wire. So suppose this is the x-axis. So far we did a shift, okay, and we did a flip. Okay, what else can you do? Okay, how about this? So that's another motion because I did something very well, the relation between the points of the original object has changed. So that's why it's not a motion. So let's say that's what I describe it. I make it number 3 a fold. Okay. So then can you think of a function for this? So once again, this is the x-axis, and then I fold it, and this is what it looks like on the y-axis. Let me, if this is maybe too visual, let me have you give you arrows. So this is 0 again. So 1 goes to 1, 2 goes to 2, 3 goes to 3. Okay, 1, 2, 3. And then there are more. -1 goes to 1. That's a fold, right? -1 goes to 1. -2 goes where? To 2. Okay, so you see what I'm talking about yet? -3 goes to 3. That's a fold, right? So once again, the orange part remains put here, and the green part is folded up. Okay, so with the origin remaining here. Okay, so you see the formula?
The absolute value.
Absolute value, that's right. Exactly right. The absolute value gives you the fold. And you can see then the interpretation of the range becomes clearer, right? So this is the range. So the half of the line now is the range. Only half because it's been folded. So the domain is everything, okay, but the range is half of it. Okay, that's what the absolute value does. Okay, so then we already have having more and more. So we have a fold, a flip, and a shift. We could certainly combine them together. Especially the first two, flip and shift. That is a very typical operation. So let's say shift and well, I think we need more. There is another one. And then once again, everything fails. So it's not a pencil. You cannot fold a pencil, so that's why I use a wire. Well, it's not a wire either. So what can we not do? So I'm looking for the fourth operation. What else can we do with the x-axis? That's the shift. I do not have an object that to illustrate it with, but well, you tell me what this is. So 0, 1, 2, 3, okay. And here I have 0 once again. 0, 1, 2, 3, 4. Okay, so what if I take 0 to 0, 1 goes to 2, and 2 goes to 4, and 3 goes to 6. How would you describe that? No, I'm asking you to describe it, verbally. What kind of transformation? No, I wouldn't say it's double. I don't know. Is it double? I don't think it is double. First of all, notice that you had your x-axis was there, and then the y-axis, the end result is the same. This is the domain, and the range is the same thing. It's still the domain is the whole x-axis, the range is the whole y-axis. Well, let me have one more. Where does -1 go, you think? Where does -1 go? -2. Okay, so is it getting clearer? What is the transformation?
Is it positive 2?
No, it's a negative. -2 goes to -4.
Well, I was just thinking because you multiply a positive by, or not a positive, a negative by a positive, it's still be negative.
Right. Yes. So okay. So let's before we do description, let's have a formula. What's the formula for this transformation?
X times 2.
Yes. Okay. So now once again, so that's the formula, right? A -1 goes to -2, and so on. Every number is multiplied by 2. That's the whole thing. What happens to the x-axis? What?
Stretch.
It is a stretch. Yes. So as you can see, it is literally we're describing a stretch. We describe algebraically. On the left, we have an algebraic description of a stretch of a straight line. So think a rubber band. And if you think about, look at it, the distance that used to be 1 has become 2. Every single one of them, not just one in the middle, but every single distance here is 2. And then after the transformation has become 2. Well, it was 1, now it's 2. That's a stretch, and once again, it is not just a stretch, a uniform stretch. It is actually typical to have a stretch that is different in different locations, that the more complex functions. But the simplest one is that 2x multiplication by a positive number and a real number larger than 1, and that number gives you the proportion of the stretch. So if I put a 3 there, it will stretch by 3. This one stretches by 2. Okay, so that gives me a bunch of possibilities. The only thing that I want to ask you, what if I look at 2x? What if I look at f of x is equal to -2x? So what kind of transformation is this? No. No, this is, let me, since it came up, this is the, so we call this what? Shrink. Yes. Shrink because, once again, 0 goes to 0, but say 1 goes to 1/2. 2 goes to 1. And so negative 1 goes to negative 1/2. Negative 2 goes to negative 1. And so as I just described, all the 1s here, these are all 1s, they become halves on the other end. So that's a shrink by factor of 1/2. So this was stretched by a factor of 2, and this was a shrink by a factor of 1/2. Okay, so that multiplication is what it does to it. It tells you how the distance between points change. Okay. So back to my question. So we have I want you to see that I do not create a new category for this. I have shrink. I have shift. I have flip. I have fold. Fold is not really a category, but it's a convenient way to think about the absolute value. And the category here, I have one category for both shrink and stretch for the time being. Why? Because as you can see on the left, it is almost the same function. It's multiplication. Okay. Okay. So what about that one? F of x equal to negative 2x. So as you can see, think about where things are going. Say 0 goes to 0 again, okay, but negative 1 goes, where does 1 go?
Negative 2.
Negative 2, okay. 2 goes to negative 4, okay. So you see where things are going, what's happening?
Maybe a stretch and fold.
No, not a fold, a flip. Right, that's the negative sign gives you the flip. So you kind of split it in two operations. First you stretch and then you flip, or first flip then stretch, doesn't matter. Right. So that's the breakdown of this transformation. This is how it works, like this. So there's a stretch, but there is also a flip. Oops. Like this. Okay, so that it is actually, if you look at the picture, it's a little bit confusing, even though I try to do my best, but it is a bit confusing, and that is actually a reason why we try to break functions into small pieces that are easy to understand. So this function that you have on the left can be split into two operations, and that is multiply by 2 and then multiply by negative 1. Okay, and then this is called a composition. We're going to consider that at length. But that's the simplest example of how this negative 2x function, which you could think about multiplication by negative 1, which is fair. I mean, it's a very easy algebraic operation, but if you want to understand what's happening geometrically, then it is easier to think about split it into even simple operation, multiplication by 2, which happens to be positive, and multiplication by negative 1, which is also simple. So then you know that the first operation will be a stretch by a factor of 2. And negative 1 is a flip about the origin. Okay, so that way you understand that more complex transformation in terms of two simpler transformations. So the algebra and the geometry are here visible. So in fact, this is 2x. You're seeing 2x right here, and where's and negative x is right there. So this is my flip. This is my flip, and this is my stretch. Okay, so if you combine them together consecutively, then that's what you're going to get. So the stretched, so think of rubber band, it has been stretched and then flipped. Okay, So in fact, I have a picture, which is what you might see a lot of once you get to things that are more complex. So rubber band, I instead of putting colors, numbers, I put colors there. So it's a colored with a strip, rubber strip with colored narrow strips indicating different locations, different numbers. And then you stretch it, and then hypothetically, certainly the picture suggests that you just do it like this, which suggests a uniform stretch. But if you look at the end result, you can see that it's not stretched. And not only it's not on just stretch, it's also, that second example, also there is some shifting. So you can simultaneously do shifting and stretching. There's no flipping there, but you can see how, you can also see, look at those strips. Some of them have become wider at a different degree. Okay, so in fact, the one on the right, the blue one has become like 3 times wider. But if you look at the pink one on the somewhere in the middle on the left, it actually has become narrower. So the behavior might be very non-uniform, and every kind of stretching, shrinking, shifting transformation can be combined into one operation, and that's it's hard to understand unless you have a formula. Okay, so that is just another way to think about functions, so that it is more visual than just a formula. So like I said again, what is that I'm saying here? This is like stretch. Here the stretch is by, it appears, at least appears to be stretched by 3 maybe over here, right? This is the transformation. But if I take this one, it is shrink by 1/2. Well, shrink by 1/2 means that it is shrink by a factor of 2. There's a language a little bit a bit awkward here, but so we're shrinking by 1/2. Okay, but then there are also shifts. You can see that both of these locations actually produce shifts. It's not right underneath it, right? So that if we take either one of those strips, it not only changes its width, it's also located elsewhere. Okay, so that is what I want to point out. So rubber band with markings, or you can think about literally if you want to have something less colorful. Imagine a rubber band with like knots or markings or knots, markings producing with numbers. So once again, this rubber band. And then you just put markings on it, like you can put literally 0, 1, 1, 2 markings on it, okay? And then -1, and then whatever you want to do with it, you can still, if a rubber band is a better metaphor because you can still shift it, you can flip it, and you can stretch it. You cannot stretch a pencil, but you can certainly stretch a rubber band. So if I say shrink it, then the same picture. Well, either I do that, or I can literally do what I say. So, and if I say it is a shrink, I could shrink. So I take this band, right? Why is it doing it? And then I'll shrink it. I lost the numbers. Let's try again. Doing it again. For some reason, I cannot catch the numbers inside of it. Let's try again. Okay, well, there you go. I shrunk it. So, so those markings are still the same, but they are located in a different location. So, not very pretty picture. Okay. So let me summarize. So y is equal x plus k shifts. You can think, certainly you can think about single number, what happens to the single number. Single number is x, and then y is what happens to it, where x ends up, okay? So that is fine. That is the basis of idea of thinking of functions. But if you want to think about a function as a whole at once, then you think about transformation of the whole x-axis. Okay, so what happens to the x-axis rather than looking at one value at a time? So ultimately, it is you cannot trace every value one at a time, but rather thinking about as a whole, function as a whole, as a transformation, as I said. So shifts the x-axis k units to the left. The tricky part is here. K. I don't want to have separate cases for k positive or negative. So it is understood. I put it in parentheses here. So k negative means right, shift right. Okay, so that way you have one formula and two explanations. So in other words, shifting negative 5 units to the left means what? Shifting negative 5 units to the left means shifting 5 units to the right. Okay. Okay, so that's the algebraic way of doing things. Secondly is multiplication. Let's do the flip first. So negative x flip. So the whole x-axis is flipped. That's very straightforward. The other one is more complex. That is this one. Okay, so this is a stretch by a factor of k. And once again, we have two categories, two possibilities. Algebraically, k could be let's assume that k is positive, but k could be still less than 1. So we know that k less than 1 is a shrink. So once again, we're using that algebraic logic. If k is less than 1, means shrink. Okay, k less than 1 means shrink. So the description itself does not say that k has to be less than 1 or larger than 1. It covers both of the cases, but the language is inclusive. So when stretching by a factor of 1/2 means what? Shrinking. Stretching by a factor of 1/2 means shrinking by 2. Okay, so we don't want to have separate cases for different values of k. Okay, so these are three main categories, and three main categories. I do not want to include as a categories, but I'll put them here as a separate list. Y is equal to absolute value of x is the fold. Okay, and then there are others that we have seen there. There might be very we have seen recently very nasty things that can happen. These just last time. The sine function and the integer value function, they do fairly strange things to the x-axis. If you think about it. So y is equal to sine x. Remember, let me refresh your memory what this means. So it's a -1 if x is less than 0, 0 if x is 0, and 1 if x is larger than 0. Okay, so then once you have a formula, you might try to interpret it once again in this geometric way. So how would you interpret this? So what does this function do to the x-axis? Well, maybe I'm getting too slightly ahead of it myself. There is a fourth category that we haven't looked at. Y is equal to, I probably should have started with this, sorry about that. So y is equal to k, a constant function. Y equal to k, constant function. What is it? What does it do? a constant function. So literally, you remember the range is one number. I'm sorry, the range is one. Yeah. So, but what happens to the x-axis? What do I do to the x-axis to end up with a constant function? No. What? What? Yeah, okay. Can you be more descriptive? What do I do with it? Yeah, that's right. So like this. So one single value. So that's a constant function. So I do not I don't have a good word. Well, how about a collapse? It collapses to a point. That's what a constant function does. Okay. So so then you can see what happens. What the sine function does. It does three collapses, but the different pieces. So it collapses the like this. So if this is my x-axis, this is what sine function does. So I will have, let's say, this is the positive part, x positive. I have this is my 0, and let's say this is my negative part, x less than 0. So then under my function sine, what's going to happen is I will collapse this one to one value, which is 1. I do nothing to the origin, to 0, so that's still 0. And I collapse the negative values to negative 1. Okay, so that's what happens. Let me try to illustrate the collapse with a maybe more dramatic way. So it's like this. Everything that's what a collapse is. You take a whole half. Well, that was dramatic, I guess. Take a whole line and you just shrink it to nothing but a point. Okay, so these are the four main categories. I intentionally did not mention in a single time what happens to the what the graph would look like. These are very simple functions, so you know what the graphs are. So we have studied them previously. That's a straight line. That is a straight line. There, they all have their representations. But this is a second point of view on functions, as well as whenever you see transformations or anything in real life, you can interpret them as functions. And so the challenge is to choose a point, choose a formula that is appropriate. So let me do one more example. Let's start with a graph. Oops. Let's start with a graph. And how about I plot something like a parabola or something like that? Well, let me take a half of it. So this is equal y f of x. So what we can think about it is, let's say, well, so can you tell me what this function does? Yeah. Can you tell me what this function does roughly? No. As a transformation, what does it do to the x-axis? Look at these three separate pieces. What does it do to these pieces? What has happened? The first piece, what has happened to the first piece? What? No, it has been shrunk. Look at it. It was longer, now it's shorter. In the meantime, the second one is almost nothing happened to it. This the one in the middle. And the last part is it is stretched. Okay, so in other words, function is an example of a function that does different things, different stretches to different places. And in fact, the rate of stretch or shrink varies continuously throughout the domain of the function. Okay? All right. So see you next week.